Hello, so today we are going to find out about nanoparticles, their properties and what they can be used for. So your keywords for today are nanoparticle and surface area to volume ratio, which is more of a phrase than a keyword, but they're both really important. So if you have started to create a glossary of keywords, then you can add those into your glossary now and find out what they mean. And also as a starter, could you please list some words that you can think of starting with nano, please? Write a few down, pause it, and then press play again so I can tell you what some are. So some words that I thought of with the prefix nano are nanometer, nanotechnology, nanogram, nanotube and nanosecond. But you might have come up with some other words. You also might have looked a few up on the internet, and that's okay as well. Now, nanoscale actually refers very specifically to something that's between 1 and 100 nanometers, and in meters, that's between 1 times 10 to the minus 9 and 1 times 10 to the minus 7 of a meter. Okay, so some examples of nanoparticles. We've come across a couple already. So Buckminster fullerene was that C60 hollow spherical shaped molecule. So that's an example of a nanoparticle. So are carbon nanotubes, which, as we've already discussed, are cylindrical fullerenes. But you can also get really, really small particles of metals, metal oxides, and silicates, which are on a nanoscale as well. And when materials exist on a nanoscale, they end up with slightly different properties compared with the properties that they would usually have if you had larger particles of them. So here we have a few examples of that. So silver, on a normal scale, it doesn't do this, but when it's on a nanoscale, it can stop bacteria from growing. So it ends up being used in sort of woven into fibers of clothing and also in deodorants to stop bacteria from growing sort of under your armpits. And titanium dioxide is able to protect us from UV light in sunscreen without leaving a white layer of sort of reflection on your skin. So it actually becomes invisible when it's on a nanoscale, but still provides that UV protection. And then other nanoparticles like Buckminster fullerene can be used as drug delivery systems like we spoke about last lesson. So a couple of questions for you now. Number one, how small must something be to be called a nanoparticle? And number two, city air is full of particles called particulates, which form when fuels burn. If you look at the picture, which is about to come up in a second, can you work out how many times smaller Buckminster fullerene is than a particulate? So here's the picture. I've put question 2 in a condensed form in that box as well. So question 2, how many times smaller is Buckminster fullerene, which remember that's a nanoparticle, so that's in this sort of pinkish section here. How much smaller is that compared with one of these PM 2.5 particulates, which is from combustion of fuels? Pause the video here and then you can unpause it and I'll tell you the answers. So the answer to question 1 is it's between 1 and 100 nanometers. And the answer to question 2 is it's around 100 times smaller. Obviously, there's a range for both of them. The nanoparticles are between 1 and 100, and the PM 2.5 particulates are between 100 and 1,000. But if you take a generalization, it's going to be around 100 times smaller than the particulate, which is found in the air. So we're going to talk a little bit more about particulates now. Particulates are small particles which can get into the lungs and cause problems. They are sort of given out by cars and lorries, and a lot of them can build up, particularly in city centres, and they can cause asthma to become worse. Now, if nanoparticles are even smaller, like 100 times smaller than the PM 2.5 particulates, they might be able to get even further into our bodies than the particulates can. Now, although it's possible that they can get into our bodies via us breathing them in, it is unlikely that they could get through our skin. So the titanium dioxide in the sun cream that I was talking about, it's unlikely that that could get across the barrier of the skin. However, if you had a lot of nanoparticles and they were gaseous and they were in the air, they might be hazardous if they were to get breathed in. Now, OCR need you to be able to evaluate the use of nanoparticles, and according to OCR, their definition of evaluating is giving your verdict on something after providing evidence which both agrees and contradicts an argument. So if we're talking about nanoparticles, then you would need to say some pros and cons of using nanoparticles for a particular use, say in sun cream or in deodorant, and then say what you think about whether they should be used or not. Now, there's going to be an example question of this in a second. So, number 3, many people worry that nanoparticles could be dangerous. Could you suggest one argument for this idea and one argument against? Now, this actually says suggest, not evaluate, this particular question. If it said evaluate, then you would need to say what you thought at the end of the question as well. So pause it and see if you can think of one thing that's for using nanoparticles and one thing that's against using nanoparticles. Okay, so if you have unpaused the video because you want to know the answer, one thing which might be a con, a bad thing of using nanoparticles, is that free nanoparticles or gaseous nanoparticles, or if they're in the air, if we breathe them in, they could get into our lungs and potentially cause health problems. However, a good thing about them is that they can be used in sunscreens to prevent health problems caused by excess sun exposure. So they can be used in good ways, but also there might be hazards to do with them as well. By the way, if you said something about them being used in deodorant as a plus, or them being used to get medicines to particular cells as a plus, that would have been fine as well. Alright, so finally this lesson we're going to talk a little bit about surface area. Now you probably have come across this in biology as well, the really important concept of surface area to volume ratio. Now in chemistry, the main thing that you need to know is the smaller the pieces of a substance are, the larger the surface area to volume ratio is going to be. So if something's a really fine powder or even a nanoparticle, then it's going to have a really, really big surface area to volume ratio. Now there's a picture here to show you how that works. So on the left hand side we've got this biggest cube here, and there are no units for these numbers, but I guess you could put centimetres on them if you wanted to. So each of the sides here has a length of 3, and then what you could do to work out the area of all of those sides is you do 3 squared. So 3 squared is the area of one side, times 6, because there are 6 sides to your cube, and that gives you a total surface area of this cube, which is 54. They've also worked out that the volume of this cube, so 3 cubed, is 27. So they know the surface area, they know the volume, and then they've done, to work out the surface area to volume ratio, they've done the surface area divided by the volume of the cube, and that's given them a surface area of volume ratio of 2. Now if we contrast that with the smallest cube here, this cube has got sides of 1. And so they've done the exact same thing here where they've worked out the surface area. So they've done 1 squared times 6, because that's the area of one of the squares, and then it's times by 6 because there are 6 sides on the cube, so that's given them 6. And then the volume is 1 cubed, which is just 1. So because this is a lot smaller, the surface area to volume ratio is going to be bigger, because this one is 6, whereas the bigger one over on the left hand side is 2. So the smaller the particle, the larger the surface area to volume ratio. Now, this is important because when particles are on a nano scale, so when we're talking about nanoparticles, they're going to have a much bigger surface area to volume ratio, which means that they end up showing new and different properties compared with what they normally act like when they're not a nanoparticle. So examples of this include gold. Obviously, you can get a big chunk of gold and it looks like a gold colour, but on a nanoscale, it can actually show up as different colours because it reflects light in a different way. Titanium dioxide normally is white, but it becomes invisible on a nanoscale. And silver, if you've got like a silver ring, for example, that probably won't destroy bacteria, but if you have small enough nanoscale particles of silver, then it can destroy bacteria. And some other things can become more reactive, which means that they're good at being catalysts, but it's also going to mean that they're more toxic. So here's another question for you. If you can't see this picture very well, by the way, then do have a look at this section in the book because this picture is taken from the book. So number 4, look at the block. Imagine making one more cut on this bottom block here. So you've got one block to start with, it's been cut into 2, then it's been cut into 4. Imagine cutting it again to make 8 equal cubes. Each side of the 8 cubes would be 0.5 centimetres long. What would be the new surface area to volume ratio? So you've got 0.5 centimetres for the side of each of the cubes. So that means you would need to work out the area of one side, times it by 6 because it's a cube and cubes have 6 sides, and then times it by 8 because there are 8 cubes. And then it actually tells you here that the volume is 1 centimetre cubed. The volume is 1 centimetre cubed for the first one and the second one and the third one, and it would be the same if there was a fourth one as well, because there's no more material there, you're just cutting it into smaller pieces. So could you pause this video now and see if you can work out the new surface area to volume ratio, and please, please, please show you're working when you do this. So if you're ready for the answer is 12 to 1. So you should have worked out that the surface area is 12, the volume is 1, so the surface area to volume ratio is 12 to 1. Well done if you worked that out. Or if you did 12 and then divided it by 1, that equally would have been fine as well. Okay, number 5, final question. Could you please give 2 reasons why nanoparticles can be more useful than large pieces of the same material? Okay, so hopefully you paused the video and you've written down a couple of things. So thing number 1 is they've got a much larger surface area to volume ratio. And the other thing that you may have written down is this means that there is a larger surface for them to be able to act as a catalyst. So you might have found that last one a little bit more tricky, so please write it down if you didn't get it. So the fact they have got a larger surface area to volume ratio means there is a larger surface for them to be able to act as a catalyst. And that's it for today. Have a lovely week, and I will speak to you soon.